What is the indeterminate structure? We have already talked about that in the axially loaded elements and in the torsional elements, and now we want to expand that concept into beams. Look at the number of unknowns that this structure has. There are 2 unknowns at A, 1 unknown at B, 1 unknown at C. There are 4 reaction forces in this beam. And in general, for a 2-dimensional structure, there are 3 equations. Some of the forces in the x direction, some of the forces in y direction, and some of the moments. The number of unknown is 4. The number of equation is 3. The problem cannot be solved just by equilibrium equations. This problem is called indeterminate, statically indeterminate. So if it was statics, we couldn't get the reaction forces at all. There is no way for us to solve this problem. But with mechanics of materials, knowing how much the element is deforming, we can get extra equations from the compatibility of deformation and solve this problem. This is what we want to do. The process, the overall concept is the same. It's identical to what we have already learned for the axially loaded elements and for torsional elements, but the equations are different because the equation that we see for beams are different from the equations that we have already used for torsional elements and axially loaded elements. So for this one, I'm going to break this down into 2 beams. One of them is going to be the simply supported beam that is subjected to the distributed load. The middle reaction support is removed, and we are going to replace that with 1 unknown force. I'm going to call that R sub B. The second beam is a simply supported beam. It is subjected to a known reaction force. Then we need to see how each of these 2 beams deforming and how can I find a relationship between the deformations. For the first beam, because of the distributed load, it's going to move downward. It's bending like this. The value of deformation at the point where the support was located is called delta B1. Deformation at point B in beam number 1. In a similar way, we can find the deformation on the second beam because of the loading acting on that. The deformation called delta B2. Deformation at point B in beam number 2. Now let me find out what are the values of these deformations. The first beam, I can find exact match. Beam deflection table. Because I'm interested in determining the deformation at the middle of the beam, which is the maximum deformation, I can just read this value. So deformation in the first beam is 5/384. Distributed load length to the 4th divided by EI. In a similar way, we can determine the deformation for the beam that is subjected to a concentrated load at the midspan. The direction doesn't matter because that just changed the sign. And again, because I'm interested in the maximum deformation, I can read this equation, PL cubed divided by 48 EI. All right, now we get to the critical point. We know that in the real structure, there is a ruler support that prevents the movement of that beam at that point. So how much should be the total deformation in these 2 split beams? If we add these 2 deformations together, they should add up to 0 because there is a support in the original structure. In other words, the amount of reaction force on the second beam should be so that the deformation is compensating for the deformation caused by that distributed load. This is the way that we can determine the value of this reaction force. So I would say delta B1 plus delta B2 is equal to 0. This is called the compatibility of deformation. Then I'm going to plug in the value and solve it for force. The reaction force is the value of the force acting at the middle part. So I'm going to replace P with R sub B. And then we can solve it for R sub B. Okay. This is the value of the reaction force. What is important for us is looking at the process by which we determine the reaction force. Again, we use the concept of compatibility of deformation. We consider the way the beams are structured, the layout of the reactions. And then based on those supports, we try to find out what should be the relationship between the deformations in order to satisfy the boundary conditions. This is the basic part that we need to understand in order to move on to more complex cases. In this problem, there is a wood beam with the modulus of elasticity of 1910 KSI, which is loaded as shown in this figure, and it's also supported by a rod with a diameter of 1/2 inch. The modulus of elasticity of the rod is also provided. We want to see how much would be the value of the force that is supported by that rod after the beam is being loaded by a distributed load of W. We can identify that there are 4 unknowns, but 3 equations exist. That means the problem is indeterminate. So we need to get the extra equation, right? Similar to the problem that we just solved. So I'm going to split this beam into 2 parts. The first beam is going to be a beam subjected to the distributed load. And I'm going to release this rod and replace that with 1 unknown force, which is the internal force in that rod. The second beam is the beam that is subjected to internal force of the rod, which I'm going to call that F1. Now, I'm going to go and calculate the deformation for each of those individually. For the first beam, looking at the beam's deflection table, the magnitude of the deformation at the midspan for the simply supported beam subjected to a distributed load is 5WL to the 4th divided by 384 EI, similar to the problem that we just solved. Now, I'm just going to go and plug in the values. Be sure to use the units that are compatible with each other. W is 900 pound per feet. I'm going to convert that into pound per inch by dividing that by 12. Length is given in as 14 feet, and I'm going to convert that into inch. Moment of inertia for this rectangle could be easily calculated. It's a rectangle, so the moment of inertia is base height cubed divided by 12. And the last part is plugging in the values into this equation and calculating the magnitude of deformation at the midspan for beam number 1. Okay, now we're going to move on to beam number 2 and determine the deformation in that beam. Deformation of a beam subjected to a concentrated force at the middle part is going to be PL cubed divided by 48 EI. We can see that this is exactly the same as the one that we just solved. So internal force is unknown. It's called F1. And I'm going to use the total length and EI into the equation and determine the deformation in terms of that unknown force in the rod. Now we need to find out the compatibility of deformation. For this problem, can I say delta B1 plus delta B2 is equal to 0, similar to the previous problem that we just discussed? No, we can't say that because the rod is also stretching. It is deforming. The deformation in the rod is calculated from the Philly equation, FL divided by EA. F stands for the internal force in the rod. L is not the length of the beam because we are talking about that rod. So L stands for the length of the rod. Area could be calculated based on the given diameter. And the length is given. I'm going to convert that into inch as we did for the previous case and use the modulus of elasticity of steel. And we can determine the deformation in terms of that unknown internal force. Okay, now we get to the critical part, which is the compatibility of deformation. In the previous case, when the beam was supported by a ruler support at the middle part, we could say that delta B1 plus delta B2 is equal to 0. What about this case? Exactly. So delta B1 plus delta B2 is going to be equal to the stretch of that rod. So I'm going to say delta B1 plus delta B2 is equal to the stretch of the rod. Here I use a negative sign before delta B2 because I know one of them is moving downward, the other one is moving upwards, just to make it consistent. And then plug in the values of calculated deformation. We note that delta B2 is a function of unknown force, similar to delta 1, which is the function of the unknown force. We get one equation that has one unknown that could be solved for F1, and that gives us the value of the internal force in that rod. So I just wanted to solve an example that has similarities, but in this problem, which was more complex, we have a different compatibility of deformation. Now we are working with the case that the rod is not providing a fixed support, but it is providing a flexible support, which is deforming because of the applied force. Now I'm going to solve another problem, very similar concept, but now we want to deal with the gap. We have a simply supported beam subjected to a distributed load, and it is also supported by a ruler support at point B. The difference here would be that this ruler support is not at the middle of the beam. So we need to be careful about the equation that we are going to use for solving our problem. Also, there is a gap in this structure. The gap would change the compatibility of the deformation equation. Okay, in order to solve this problem, we need to split that again into two parts, similar to the previous problems that we discussed. First, I'm going to consider the beam that is subjected to the distributed load. But in this case, we are not interested in determining the maximum deflection, but we need to determine the deformation where that support was located, which is in this case closer to the left side. I'm going to call that delta B1. Then the second beam would be the beam subjected to the reaction force at that point. It is bending upward, and the magnitude of deformation is called delta B2. Let's calculate each of those one by one. For the first case, we are not seeking for the maximum deflection, but we need to use elastic curve because the deformation is not determined at the midspan. It is giving the deformation at any point which its coordinate is given by x. The total length of the beam is 10 meters. X is the distance of the point at which we want to determine the deformation from the left support, which is 4 meters. And EI is given in Newton and millimeter. But I'm going to convert that into kilonewton and meter to make it consistent with the rest of the data. And yes, the unit conversion is tricky for these types of problems. You can convert either to Newton and millimeter, or similar to what I did here, to kilonewton and meter. Either way we go, with the final answer should be the same. The next one is determining the deformation for the beam subjected to the concentrated force. This one is the maximum deformation, which is determined from this equation. Length is the same. A is the distance of force to the left side, and B is the distance of force to the right side. And I'm going to plug it in. Note that the amount of force or the reaction force is unknown. All right. Now we get to the critical part. What is the compatibility of deformation? Can I say delta B1 plus delta B2 is equal to 0? No. There is a gap, and I need to take care of that. So, assuming downward is positive, delta B1 gets positive sign, delta B2 is upward, gets negative sign, and that is equal to the value of the given gap. Just be sure that you are using the right unit, and from that, we can determine the value of the reaction force. In my case, is 98.4 kilonewton. So, I wanted to solve a series of problems starting from the case that the problem was indeterminate, but there was nothing else other than that. The second problem was the problem with flexible support. The rod could stretch, and we need to figure out what is the compatibility of deformation. The third problem that we discussed is the case where the gap exists. So we covered 3 different types of problems that we could talk about in this topic. And with that, we are done with this chapter. Definitely you need some extra practices that you can find them on the post-class problems. You guys have a good rest of the day, and I will see you on Friday.